Okay, so what we're going to talk about today are a series of properties called colligative properties. And there's actually 4 of them. And we'll talk about 2 of them mathematically, and then the other 2 we'll just kind of talk about in passing and not worry about them. And the thing that they have in common is they're properties that depend not on the substance dissolved, meaning the solute, but on simply the number of solute molecules. Meaning, really, technically, this is not about chemistry. This is simply a function of the number of molecules that are dissolved from one substance in another. And so basically they depend on numbers, not identity. And then there's a couple caveats that we want to put. The first one is that our solute has to be non-volatile. Well, that's a vague question, meaning can you be more specific? And I got to be, so for instance, if I have solution A, which has, say, 50 atoms of A in B, and if I have a second solution, we'll call them solution 1 and 2 since we're using letters, and I have 50 atoms of C in B, it means that these 2 solutions are equivalent, meaning they're going to have the same colligative properties. Because what it cares about is the number of atoms matter, but the chemical ID does not. So it doesn't matter whether it's A, C, or B, A or C dissolve. Therefore, A and C don't matter. So they're properties that purely depend on something being dissolved in something else and not what we're dissolving it in. So do you guys know what non-volatile means? Okay, so non-volatile means it has a very low vapor pressure. And we're going to say on the order of 0. And it also depends technically on the solute breaking apart into ions, so the number of ions formed. But again, we're going to ignore this. Meaning we're trying to get it to be as simple as possible and just focus on part 1, which is the number of atoms in solution, or the number of moles, and not worry about the exact identity of it and whether it's going to form ions in solution. Those are things that we can add to make the problems more difficult, but again, we're going to ignore them in this class.
I'm sorry, it says for 3 it's the solute.
The number of ions formed. Meaning, like for instance, if sodium chloride dissolves, it forms Na plus Cl minus, right? But if, for instance, CO2 dissolves in water, it just forms CO2 aqueous, meaning that the number of ions formed technically matters. Or if I have, for instance, Na2 CO3, then that breaks apart into 2 Na plus ions plus 1 CO3 minus ion, meaning I don't care about the number of ions in solution. We're just going to keep it simple and talk about the number of atoms.
Why?
Why?
Just, no. Continue. Well, actually, could you slow down?
So colligative properties don't depend on what chemical is being dissolved in it. They only depend on the number of atoms. And there's 4 of them. The first one is vapor pressure. Yes, vapor pressure decreases. Okay, you guys are not, seriously, Colligative properties, there's 4 of them. This is the definition of colligative properties. I haven't even talked about the number of colligative properties. So here, we'll even make it more obvious. Property 1. So vapor pressure decreases as the number of atoms increase. So what we're saying is that if I've got 2 beakers, and this is compound pure A, then, you know, I'm going to have a certain vapor pressure, right? And if I have a second beaker that is a mixture of A plus it's got some extra particles in it, so we'll call these B's. So that's my impurity. Then the number of particles in the vapor phase decreases. So as the number of atoms of the impurity, I guess we can say, increases, then the vapor pressure of that decreases. And the reason for that is that basically here we've got particles of B that decrease the surface area, therefore they decrease the vapor pressure, and simply that the impurity molecules can't vaporize. And so there's going to be less A molecules in the vapor phase. And so what that means is that if we take a line, and this is the vapor pressure, because you've got something else in the beaker, so the surface area, the amount of A there decreases.
Surface area of A.
Yeah, surface area of the A, because that's what we're talking about. That's the major component. So vapor pressure has units of millimeters of mercury, and if I plot that versus temperature, we had this figure in the book. And so this is my pure substance, right? So what happens is if I add an impurity, the vapor pressure decreases, and so that means the vapor pressure goes like this. So this is the vapor pressure with an impurity. Somehow I pushed a button. I don't want to do either. I don't know why it decided to quit on me. We'll just start over. Okay, so the first property is that if I add something to a pure solution, it decreases the vapor pressure. The second one is what happens to the boiling point. So we're comparing a pure solution A versus a solution that has some impurity in it. So the vapor pressure of the pure solution, when you add the impurity, decreases. So the more atoms you add, the lower the vapor point goes.
So the first beaker has a higher vapor pressure.
Yes. So high vapor pressure, meaning there's 5 little molecules. This has a low vapor pressure because there's only 3 little molecules in there.
Pure substance applies to that dotted line or to what?
Yeah, the red mark and the red statement apply to each other.
Yeah, but pure substance goes
To the blue line, because it's in blue. You guys are much smarter in the mornings.
I think it's this board. I think it's,
Too far away?
yeah, it's something about maybe this form.
then you're kind of in a hurry, doesn't let us say.
I can't hear you. Property what?
You're so quick too.
I'm going to have to just start taking Valium.
Weather doesn't help. We just ate lunch. We got a lot of excuses, James.
So property 2 then is that the boiling point increases as the number of atoms increases, or as the amount of the impurity. And so if we draw that graph again, meaning here's my millimeters of mercury, that's my vapor pressure, this is temperature. And if this is 760 millimeters of mercury, we know that for a pure substance it goes like this, and this represents the boiling point, right? And so here, if we drop it down, we'd say maybe the boiling point, if it's water, is 100 degrees Celsius. And then if we add that impurity, remember, that causes my solution to decrease in vapor pressure. So this is the impure solution. And so notice its boiling point is over here at some other number, say 101 degrees Celsius. So the graph is not to scale.
Can you give me an example of an impurity?
Name any substance that's not water.
Oh, really? So like sand.
Sand would be an impurity. Now, technically it actually has to be something that'll dissolve in the water, so not any substance will work. So sodium chloride or magnesium chloride or
Oh, okay.
any chemical that dissolves in water is what we would consider an impurity
Even
or a
if that
solute.
chemical has a lower boiling point than water?
Yep. Now, we also said that it has to be non-volatile, so it technically should have a higher boiling point than water, right?
Okay. Because it has to be non-volatile. Okay.
So the impurity has to dissolve. It has to have a high vapor pressure, which means that it's non-volatile. So good examples are basically any ionic compound. So property 2 is as the number of atoms increase, the boiling point increases. Sometimes that's called boiling point elevation. So you remember when you brought up the fact that spaghetti, they add the salt in there so it'll cook faster is what it is? Technically that's true because the boiling point of the water will be higher, and so since there's more heat involved, the spaghetti will cook faster. But to be honest, with the amount of salt you add and this very small change in the boiling point, I can't imagine that it would be any measurable difference in the cooking time.
Cook the pasta faster, they say the water will boil faster.
Oh, it boil? No, it actually boils slower because you have to add more heat to it.
Because you're adding impurities to it.
Yep. So
Son of a bitch,
these
liars.
Italians know crap about chemistry.
Nobody anywhere knows crap about chemistry because it's
It
hard.
doesn't have anything to do with water boiling fast, because otherwise they will be boiling water with salt for tea too. It's for spaghetti not to stick together.
No, that's why you put eel in it. Huh? You put
So,
eel in the water for spaghetti.
Property 3 is about the freezing point, and the freezing point decreases as the number of atoms increases, or the amount of the impurity. And it's for the same reason that the boiling point decreases. So if we take a look at it, and we have sort of 0 millimeters of mercury here. So notice I'm changing my graph just a little bit. We can draw a diagram that looks something like this. And so here is my pure substance. And when the vapor pressure is 0, this is my freezing point. So for water, this would be 0 degrees Celsius. And if I take my impure substance, and we'll do that in red again, remember that decreases things. And so it's going to look like this. And then it's going to match up with that line. And so notice here now my freezing point is lower.
So if you put salt in your ice cube tray, you can go freeze faster?
Well, technically it would take more energy. You would have to take more energy away from the water so it would freeze slower. 0 millimeters of mercury. So this is my impurity. So notice that this all stems from the fact that the vapor pressure is decreased, that we lower that line. Lowering the line means that we increase the boiling point because the boiling point moves over here, but lowering the line means that we decrease the freezing point. So what do we do for the roads in winter? We put salt on them, right? Unless you're in Utah. Utah uses salt. Who uses sand around here? Anyway, the reason for putting the sodium chloride on there is that you decrease the freezing point of the water, and so that means on a day where it might not melt normally, it would now melt because the freezing point is lowered. And so it keeps the roads ice-free for longer because it lowers that freezing point. It has to get colder in order to freeze the water on the roads.
How much?
The freezing point depression is generally larger than the boiling point elevation. And we're going to show mathematically what that means in a minute. So don't worry about that. We're going to come to some mathematics in a minute. Okay, property 4 is one you guys have all heard of. You just may not have known it as a colligative property. And I shouldn't say everyone's had this, but if you've had biology classes, you've generally come across it. It's called osmotic pressure. And so the osmotic pressure increases as the number of molecules or the number of atoms dissolved increases. And so the way to think about osmotic pressure is if we had a beaker and we put a membrane in it that's got lots of little holes. So this is what we call a semi-permeable membrane. And what it does is it allows small molecules to pass through. And since 99.9% of the time we're talking about water, we'll just kind of limit it to that. And it blocks large molecules. And so if I've got water in here, and I've got a semi-permeable membrane, the level will be the same on both sides. Now the process of osmosis is the diffusion of water from low concentration to high concentration. So the reason you normally hear about this in biology is because the cells have a certain pressure on them. And if we change the pressure around those cells, we can have things either being sort of forced into the cells or forced out of the cells. Or the other way I like to think about it is, has anybody made pickles? What do you make pickles with? Vinegar, and it's a heavily salted solution usually, right? And so that salt forces the water into the pickles, right? Or out of the pickles, I forget which way. So if you've made pickles, you've done it. Or one of the things that we always have to worry about when we have blood transfusions or anything else is their solutions have to be isotonic. That's so that water doesn't flow from or into the cell, either swelling it up or shrinking it down. So what that means then is if I take that very same beaker and I add sugar in one side. Now sugar's big and it doesn't allow it to move. And so what that's going to do is that's going to force water to flow this way. And so what happens is the water on one side of that membrane is higher than the water on the other side of that membrane. We force water from the solution that has low solute concentration or high solute concentration to the solution that has low.
Was this kind of like the YouTube?
Actually, wait, I got this backwards. Oops. Water is going to flow this way. Is this kind of like what YouTube video?
No, YouTube video like YouTube is
Oh, YouTube, like not, yes. Yes. Sorry, I was thinking videos, and I'm like, what the hell does this have to do with YouTube? Yes, so you can think about it like a YouTube.
Oh, not YouTube.
So we go from low solute to high solute. And what that does is that difference in height of the water, that's what we define as osmotic pressure. So, for instance, if we have what we call a hypertonic solution, that means that the well, actually, let's define it this way. We'll use a real life example. It's probably easier. So if we talk, well, I'm going to use a new slide because I'm going to run out of room. So if I talk about red blood cells, they have a concentration that is about 0.15 molar NaCl. So if I have what's called a hypertonic solution, that means that my solution is greater than 0.15 molar. That means that water leaves the cell, and that causes what's known as crenation. Or basically, they shrivel up. Well, I got to be honest, I can never remember which word is which, and so I always just say shrivel up or swell, because shrivel up and swell has a visual image with it. The word crenation means nothing to me.
Shrivel up and swell are two opposite things.
Right, that's what I'm saying. This one is shrivel up, right? If I have a hypotonic solution.
Okay. Well, I thought you were saying it shrivels up and swells. And there's the same thing.
That's
So
where my...
tonic water is just salt water? Or it's just salty soda water?
I don't know if the tonic has anything to do with that. I think the tonic might...
Well, it is different.
Yes, I realize this. I'm just saying that I don't know if the term tonic in water like that has anything to do with hypertonic or hypotonic.
No, I don't.
It means shrivel up.
What is sugar?
Shrink. So if you've got a normal cell, what's going to happen is it's going to shrivel up like this as the water leaves the cell. If I have a hypotonic solution, that means that it's less than 0.15 molar. That means that water flows into the cell. And that leads to a term called hemolysis. And see, again, that word means nothing to me, so I simply say it swells or enlarges. And both are bad. You don't want your cells to be in a hypotonic solution, and you don't want your cells to be in a hypertonic solution. What you really want is an isotonic solution. And that is when the solution is equal to, for red blood cells, 0.15 molar, and then there's no effect. Meaning water doesn't flow into the cell or out of the cell at an enhanced rate. So how many people have contacts? Now, when you soak your contacts overnight, what do you put it in? Contact lens solution, right? And if you read that, you'll read the contact lens solution is isotonic with the moisture, the tears in your eye, basically. And that if you put them in pure water, eventually you'd probably, I'm going to guess, pure water would have less of a concentration, so you're going to swell them up. Water is going to flow into
When
them.
you get piercings, the solution you're supposed to make is supposed to be isotonic.
How the hell do you know that?
That was the first piercer.
Wait, when you pierce, you don't. Why are you? Don't you just jab someone with a needle? Why?
Clean it.
Oh, clean it. Yes. I'm like, why the?
I thought it was just like rubbing alcohol.
No, you're not supposed to use alcohol. You're supposed to use the same solution as your tears. Because it's your body is like the same thing.
Okay, so mathematically, we can describe boiling point elevation and freezing point depression pretty easily. So we need to define one new term That is molality. Now, the only bad thing about molality is it's a lot like molarity, so we have to be very careful when we're talking about them to over-enunciate it so we know which one we're talking about. The other annoying thing about molality is it has a lowercase m as its symbol. And so molarity has an uppercase m. So you also have to be careful when you're writing it to be clearly distinguishing lowercase and uppercase m's. So penmanship counts. And what molality is defined as is kilograms of solvent per mole. Wait, I got it backwards. Moles of solute all over kilograms of solvent. And molarity is moles of solute per liter of solution. So notice one is moles per kilogram, one is moles per liter. And the reason for that is that kilograms of solvent is temperature independent. Meaning mass doesn't change as temperature increases or decreases, whereas volume is temperature dependent. And so the effect is usually pretty minor, but it's, worth, well, that's just the way things are defined. So we can have what's called a, well, okay, so molality is what we're going to use in our equation. And then the equation for freezing point depression, do I need to slow down?
Yes. You said freezing point depression?
Right. So the idea is that we want to be able to calculate how much the freezing point changes, and we're going to want to calculate how much the boiling point changes. Yes, Oksana?
So molarity is moles of solute over solution means solvent and salt.
Right.
And molality is just the solvent.
Yeah, there's a small difference there, but not enough for us to matter most of the time. So for the freezing point depression, the change in the freezing point is equal to mkf. So m is what we just got done talking about, molality. Kf is a constant, and it's called the freezing point depression constant.
Hey guys, can you focus? I tried, but it's not very fun.
And this is not on your cheat sheet, but it's going to be given in your book, or I'll also give you the value on an exam, meaning don't bother memorizing it. What the freezing point depression constant really is it's essentially the same thing as S in Q equals ms delta T. It's merely a constant that we look up all the time. So for instance, Kf for water is equal to, where do I have it written down? 1.86 degrees Celsius per kilogram of solvent all over moles of solute. So notice that it has a bunch of units with it because they have to cancel out. Now if we compare that, for instance, Kf of a compound called benzene is equal to 5.1 degrees Celsius per.
Can you slow it down just a little bit?
If I had a book in front of me, I'd tell you what page they're on, but I don't remember, and I don't have a book because I gave mine all away currently.
The moles of solute in the
Yes, so it has the opposite units of molality because the units have to cancel out. We'll show an example here in a second. What?
The second one is.
It's of benzene. Mostly I'm putting a second one there so that you have a comparison, meaning the values are different for each compound, just like S is different for each compound that we talked about. What is what? What is it? It's C6H6. It's not gasoline, really.
You have to express yourself in such vulgar language.
You need to write down
Okay,
damn
why
thing.
don't you guys all shut the hell up so we can get done with the lecture? I mean, seriously, I imagine that if you're one of the people that isn't blabbering, it's very tough to follow things along if everyone's talking.
Blabbering.
Yeah. So an example question would be like, if we have, say, our radiator has 50% ethylene glycol, which is C2H6O2, and it's 50% water. We can say basically what is the freezing point of the solution. Meaning, how cold does it get before your radiator freezes up and you can't start your car? So here what we're going to say is that ethylene glycol is my impurity, and that water is what we would consider our solvent then. And so if we look at it, we know that delta TF is equal to mKF. Well, we can look KF up. That's just 1.86. So what we need to do is calculate molality, which remember is moles of solute all over kilograms of solvent. Yes, that's KF of water, because that's our pure substance, right? That's the solvent. So let's assume that we have 100.0 grams of C2H6O2 dissolved in 100 grams of H2O, meaning that's a 50-50 mixture, right? So to get the moles of solute, we have to start with our 100.0 gram. Well, actually, I'll do it on its own line. Otherwise, I might run out of room. Well, actually, it'll work. So if we start with our 100 grams of C2H6O2, I need to be able to convert that to moles, right? So how do I convert from grams to moles? Yeah, 62.07 grams of C2H6O2 is 1 mole of C2H6O2. So this is just the molecular weight of our ethylene glycol. And since I want kilograms of solvent on the bottom, that means I can start with my 100 grams of H2O on the bottom. And for that, I just need to convert from grams to kilograms. And so we know that 1 kilogram is 1,000 grams. And so if I plug that into my calculator, I better get 16.1. And notice that the units I'm left with, grams cancel, grams cancel, grams of this, I'm left with moles over kilograms. And I don't have room to write solute and solvent. And
Supposed to be moles over kilograms.
yes, moles over kilograms. And so notice that if I do delta TF equal mKF, well, M is 16.1 moles of solute all over kilograms of solvent. And if I multiply that by KF, which is 1.86 degrees Celsius per kilogram solvent all over mole of solute, notice that my units all cancel except for degrees Celsius, and when I plug that in, I should get 29.9 degrees Celsius. So what that means is that a 50-50 solution of ethylene and glycol has a boiling point that's basically 30 degrees lower than the boiling point for pure water. So if I look at, well, I'll wait for a second.
So it's the unit for the 1.86 degrees Celsius
Per kilogram solvent per mole solute. That's why I was saying that back here it has that weird set of units because it's got to cancel out the units from the molality. Kind of like how specific heat has units of joules per gram degree Celsius because it's got to cancel out all the right units, right? So notice that our constant, the units that are associated with it, it's really just a conversion factor. So what that means is that pure water freezes at 0 degrees Celsius, right? Which means that impure water, or I should say the 50-50 solution, will freeze at minus 29.9 degrees Celsius, which is probably safe for Rangeley. Usually doesn't get down to minus 30. What? So the negative, remember, is that's the change in the freezing point, right? So the change in the freezing point is 29.9, and we know that freezing point is depressed, so we have to subtract it off to get minus 29.9. Just like if we calculate a boiling point elevation for water, we would add it to 100 degrees, right? So if we do that same calculation, for instance, if I take a 50-50 mixture of ethylene glycol,
Is a new one?
yeah, plus water, now I want to calculate the boiling point. So the equation is the same. The change in the boiling point is simply mkb. And so here kb is simply our boiling point elevation constant. Meaning it's exactly like a freezing point depression constant, but it's a different number. For instance, kb for H2O is 0.512 degrees Celsius per kilogram of solvent per mole of solute. And Kb, for instance, for benzene, just as comparison, is equal to 2.53 degrees Celsius per kilogram of solvent per mole of solute. So Kf and Kb values are different, meaning how much the boiling point is increased is different from how much the freezing point is decreased. Otherwise, the whole math for the question is still the same. So I can actually skip all those steps where I calculated the molality of my solution and go straight ahead and plug it into the equation and simply say that delta Tb equals mkb. Well, we've already done this, so we already did this. We know that was 16.1 degrees Celsius, or I'm sorry, moles of solute all over kilograms of solvent. And now we multiply that by 0.512 degrees Celsius per kilogram of solvent per mole of solute. Notice my units cancel out nicely. And I didn't bring my calculator again because, well, I'm lazy. But what's 16.1 times 0.512? Brittany's got my back again. She's always prepared. 8.24 degrees Celsius. So that means for a pure solution, the boiling point for water is 100 degrees Celsius. For the impure solution, the boiling point then has to be 108.24 degrees Celsius. All done? So again, freezing point depresses, so we subtract it from the freezing point. Boiling point elevates, so we add it to the boiling point. And then we don't have formulas for osmotic pressure. We don't have formulas for vapor pressure. Those are more complicated situations. We won't worry about them. Meaning, we'll understand that the vapor pressure decreases. We'll understand that the osmotic pressure increases, but we won't care about calculating how big the increase is for anything.
So will we always calculate the pure solution and the impure solution?
Well, not really. I mean, the pure solution is just whatever it is, right? Meaning the boiling point of water is 100 degrees Celsius. There's no calculation involved. We just have to know what it is. For the impure solution, that we can do the calculation on, since we know the freezing point depression or the boiling point elevation constants. So what that means is that homework 14C should be due Thursday at the latest. And then what we'll do for the rest of the week is we'll start lab, and we will work on lab, and we will have a lecture on chapter 15, and we'll have our test in chapter 14 and 15. And then Thursday night, we'll have a review session for chest is on chapters 13 and 14. For chapters 13 and 14. And then next week, basically, we'll just lecture and we'll have a test. On chapter 15 and 16 on that Friday. What? Yeah, we'll lecture and review. So lecture, plus we'll have to schedule a review in there. So we won't have a lab next week. Jess? So finals week, and I've got it laying on my desk, and I'll go check it in a second, but I'm pretty sure on Monday at our normal class time, so 8 to 10, is going to be chapters 1 through 8. And then I'm pretty sure Tuesday it's 12:10 to 2 o'clock or something. I don't know. I'll go look. I said I was going by memory. Tuesdays is from 1 to 3, so they do give you a lunch break in there. That's nice of them. What did you say? Which days? The finals week, or?
No.
I said we're going to lecture, so that means that all 4 of those days will lecture and or review.
So we're doing chapter 15 and 16.
Yes.
Lecture.
And what you'll find is that about half of the material in chapter 16 is actually really good review for the final. and 15. And then 16's a new thing, but it's something that we should at least know going into next semester.
And then 1 to 3, right?
1 to 3.
And that's it?
Yep. And we'll probably have the finals. I think we should be able to just have them over here in our normal classroom. I don't think there should be another class.
Will they take us 2 hours?
It depends. If you don't know anything, it only takes 5 minutes. You just put your name on and leave. If you know a lot, then it maybe takes longer.
Points to your name.
Yes, you can get 1 point.
Are they on the scan phone?
No.